Okay, I start with this slides because today I'm going to talk about the economic dispatch with equality constraints. During the lecture of last Friday, we talked about economic dispatch without any inequality constraints. So we do have a single equality constraint, which is exactly the power balance. But today we're going to add inequality constraints, which means the generator's outputs will have a lower limit and upper limit we need to consider. Just quickly go over how we're going to address inequality constraints. So we know if we have the cost function, which is the total cost for generating power, and we have equality constraints. For our economic dispatch problem, there's only just single equation. There's just only one. The k is just one. It's just single one. And then we can add some inequality constraints, which means something is less or equal to 0. So this just to model how we can limit the output of the generators not to be too high or not to be too low. So the idea is to solve this problem is to have this Lagrangian function L. The first is just original cost. The second is just the penalty we're going to pay for violating the equation, right? Equality constraint. And second is just the penalty we're going to pay for violating inequality constraints. So if we only have just cost itself and together with equality constraints, this is very simple. We just find the stationary points of L by calculating partial L, partial F, partial X, and partial L, partial lambda. Then we'll check the values, the cost value at each point to find which is smallest one. But if we involve inequality constraints, we definitely can also deal with those constraints similar to the constraints, equality constraints, by introducing the mu. Here, they also Lagrange multipliers. So we multiply this mu by each the expression of inequality constraints. So we also add those components into the new cost function L. But there will be two condition possibility. First is each inequality constraint is satisfied, fully satisfied, which means it's the value is within the boundary, not reaching the boundary. The second is just at this boundary. So which means we need to deal with them differently. So there will be the so-called KKT conditions. K conditions is proved to give you a set of either equations or inequalities to help you to fully represent what happened with those inequality constraints. So I remember I used a figure to try to give you some idea why the KKT conditions will fully cover the inequality constraints. But here you can just remember the KKT conditions include 3 items. Okay, the first item is just the inequality constraint itself, right? So this is simply just from the original formulation. So that's number 1. So number 2, you introduce the Lagrange multiplier mu. The multiplier, because physical meaning is some penalty. So penalty here will not be negative. It can be 0, but it usually will be positive if violate the limit. So that's number 2. Number 3 is very important. Number 3 is just the product of the expression u, which is from the inequality constraint, and the mu will be 0, always 0. Okay, so you can have both be 0. You can have one to be non-zero, but the other one will be 0. So they together the guarantee. So those 3 together, defined by the K condition, will fully represent what's happening here. Then starting from now, we just forget about the original formulation. Let's just go ahead to solve everything in this box. So the yellow items actually from the gradient vector to be 0 of the L function, and the The green part will be from this KKT condition. Okay, so if you want to solve very highly dimensional problem, like you have a tens of thousand generator to dispatch, you definitely want to just program your code or your solver based on the yellow and the green expressions. But fortunately, in this class, we only just want to learn the flavor about the enormous dispatch. We're not going to deal with a really high dimensional problem. Even for the course project, you only just need to dispatch about 5 generators, which is about same size of any examples in this textbook. So fortunately, we don't have to program for the general cases using those yellow and green items, but they're still very valuable for us to understand what happened. So here, we can replace the KKT condition by simply 2 scenarios. The first scenario is just the multiplier to be 0, and this U will be negative, right? Or second is the mu is positive, but U has to be 0 because their product has to be 0. So those scenarios seem to be very easy, much simpler or much easier to be understood compared to everything here in the K condition. But believe me, for the K condition, that's very important if you really want to create a very general code. But in this class, if you don't fully understand K condition, you want to check for scenario 1 or scenario 2 to make sure you cover everything. That's totally fine. Okay, right? So now we're ready to go to the enormous dispatch. Question?
Study of the lambda again and also the mu in the logarithm.
Okay. So they lambda and the mu, they're both called Lagrange multipliers.
Oh.
Okay, they're just multiplier, but it just have different meaning. So the method, the total method is called Lagrange multiplier method. The idea is you have a regional cost function, right? So if you don't have any constraint, that's easy. You just solve the gradient vector. The gradient vector has to be 0. We mentioned there's step 1 to find the gradient vector to be 0, but that can be minimal points, maximal points, or the saddle point, but you can check which one give you the minimal count. That's easy. If you add equality constraints, this one only, so instead of calculating gradient vector of F, you calculate gradient vector of L. L actually includes both X and lambda. Okay, because there's no room for the equality constraint to negotiate. That become part of your formulation. Okay, the third step, if we also add inequality constraints. Inequality constraints compared to equality constraints, it add a little bit thing different because inequality constraints also include equality right here. But there's also another possibility which is not equal. So we have to treat them differently. We have to separate into a 2 scenario. Okay, so if it's equal, that will be exactly same as the equality constraints. So we'll have positive multiplier, which means penalty. But if it's less than 0, which means that multiplier doesn't need to exist. So that makes things a little bit more complex. So you cannot calculate like just by single gradient vector. You still need to calculate the gradient vector, but here you have to check either use KKT condition, which means you include this part together with your gradient vector, or you check all possibilities. Make sure every possibility is covered. Possibility means for each inequality constraint, it can be negative or 0. If you have a multiple inequality constraint, let's say if you have 100 on the generator, so each generator, the generation need to be less than limit or be equal to limit. So you figure out how many possibilities you have. You have unit number 1 reaching limit, but not the other not. Or number 1, the 2 reaching limit, but the other not. Together today we'll show why there could be many possibilities. Okay, because just in this section, we don't deal with high dimensional problem. We only deal with generators of 3, 4, 5. So even you treat all possibilities, that's not allowed. It's still doable. It can be done on the paper. But if you deal with 1,000 generator, you don't want to go this way. That's too complex. So this is much simpler. Because there are some technique to help you to solve those together for you. No matter the dimension can be very high, the scalability can be much better than what we're doing today. But the focus of this class is just give you a flavor idea on what economic dispatch problem need to address. So we're fine. So you can try to program some solver, smart solver based on numerical method or even AI to try to give you good solution of a bunch of this one, no matter how many constraints you have, and always call that functions to solve your homework problem. That's good. That's definitely much better than what I require you to learn here. But that is also okay. You only just use that one. Okay. Any other question? All right, so we are ready to move on to the problem. Oh, another thing is let's quickly just go through what still the cases without limit. If the economic dispatch only have equality constraints, which is the power balance, the total generation is equal to the total load. So which means we only just need to solve the gradient vector of L to be 0, right? So the solution can be found analytically, fully analytically, which means there are 2 steps you can do. Those are the 2 formulas from the textbook. And when you work on the homework problem, there's one problem asks you to use those 2 formulas to directly solve the problem. So you know what those formulas are if you don't have the textbook in hand. Okay, so for this case, that's very simple. Only this one slide, you just do step 1, step 2, step 3. Step 1, since you already have the cost function for each generator, you know alpha, beta, gamma, everything, right? So you can directly calculate step 1. Step 1 will give you a lambda, which is the equal incremental cost, which is like a price of the market, like market equilibrium. Every generator need to agree with the same price. So like a negotiation. So if there's many power plants, some power plant may think probably I can, if I know this is my market price, maybe the dispatcher assign this price to me, ask me to generate electricity at this price. What if I make the price slightly lower? Can I generate more? Okay, there could be some there's some gaming inside, but this tell you for eventually, no matter what dynamics it can have in the market, eventually every generator has to agree with the same price. Otherwise, the market is not stable. So that is the price you calculate, and give the price to this formula that tell you how much generation you're going to provide. Okay, and then when you know each generation, you plug into the cost function, you know the total cost. That's simple. That's very simple. Another homework problem. This is just an example showing simply working through the step 1, 2, 3 to get the lambda, pi, and cost. So what happened is, so each lambda, before we determine the value, each one is a linear function. So which means every generator can have a different price function. Like for instance, this one, when we increase the P at the same speed, this cost increase slower than the other 2. So this is like cheapest units, and this is more expensive unit. But when the 3 units together power the same load for 800 megawatt, the step number 1 determine a horizontal line. So that is the price, $8.5 per megawatt hour. So it intersects with those 3 lines, and they will operate at exactly the same price. But what are their differences? So for cheaper unit, because it's cheaper, the intersection point indicate the higher output. So this unit can generate 400 megawatt power. This second unit can generate 250, and the most expensive one only generate 150. So that's fair. Okay. So if any unit change, like if I do some upgrading, add some high technique module into the third unit to make the third unit be slightly cheaper. So what happens is that line will become, let's see, the line will shift, which means to generate the same amount of power, the price actually go down. So what will be the new equilibrium? So if we check the intersection points now, the total, the three together will now be 800, right? So if you calculate, they say 250 is 400, this one become 200. So total become, the total will be 850. Bigger than 800. So which means if I make any change on the price curve of any unit, so all the units have to move to adjust the output to reach. If we maintain the same load and change, so what happened is that there will be this curve will move down. So that will make a new intersection point together to still be 800. So eventually they still operate at the same price. Okay, this is the dynamic I was talking about. This model represents the system. All the units will be fully dispatchable to the operator. And the operator knows full information about the price of any unit. But today, in many areas in the US or North America, that's called the deregulated power system. Deregulated power system, which means the operator doesn't know exactly the cost. The owner of the generator, you provide this cost information. It's up to you. You can provide this curve or that curve, but finally the operator tell you what price what output you need to generate electricity. Okay, so you can play with the market, but eventually, so there will be some dynamics. Back to around 2000s, when the electricity market was deployed in the first few years, there's something happened in California because the market was not designed back then. So there's called California crisis because the transmission owner, the owner of the generator figure out if they can suddenly increase the price, that can make their equilibrium to be very high, so they can gain much more benefit. So things like if I have 10 units, by shutting down one unit, the market, the system will have not have enough generation, so user will want to pay higher price for my remaining 9 units. Okay, so the total profit is much higher than letting my 10 unit to generate. So that can happen, but later they figure out how to avoid such things. But today, each generation owner they need to report this curve, and the system operator, which is the independent system operator called ISO or RTO, we have learned from the first section, they decide the equilibrium point. So they're going to solve the economic dispatch problem. At the end of a Friday lecture, we also show this one using the Newton-Raphson approach to solve this problem. In this case, we don't go through the step 1, 2, 3, but we will take iterations 1, 2, 3, right, until it converts to a solution. You can give an arbitrary price. This one doesn't have to be same as the final equilibrium price or the equal incremental price. It can be very different, very far away from the price, but no worry. So this approach is, I have this initial price, I just plug in this formula. I just assume this is our formula from step number 2, right? Instead of give it the accurate price, I just gave you arbitrary value. So it will tell me some output. Then I plug in this output into the power balance equation. So definitely the equation will not be 0. So there will be some gap. Then using the gap, I do iterations based on the Newton-Raphson approach. It will tell me something I need to update for the price. Then I go to the second iteration. So for this case, even the initial guess is very bad, but it gave me how much I need to update. I need to go up by 2.5. So we know by going up 2.5, I get the balance to be held. So finally, we solve the problem. Only by 1 or 2 iterations, we find the final solution. So that's exactly same as the solution from previous slide. Okay, so you have 2 approaches to solve enough dispatch. First, you can use those formula, and second, you give it some initial guess and just iterate, and after some iteration, it will reach a final solution. So for the economic dispatch problem without inequality constraints, which means all the generators have no limit, both approaches are fine. But when we move to the new problem with generator limits, this problem is better, okay, because it can iterate. All right, so now let's start talking about the formulation. So we add those inequality constraints. Basically, we assume every generator has an upper limit, which is a PI max, and a lower limit, which is PI min. There's no room to negotiate. If you change your output and which reaches the either limit, you need to stop there. You cannot go beyond that limit. So this one is equivalent to the PI minus maximal is less or equal to 0, or the minimum minus the output is less or equal to 0. Why do I want to change the inequality in this format? Because in original formulation, we have U is equal U is less than 0 or equal to 0. So this is just our standard form, right? Remember earlier we have this is our standard formula, U. Okay, so we have 1 equality constraint and 2 inequality constraints. So next step, we create the L function, which has original cost, the penalty due to the equality constraints, and penalty due to the inequality constraints about the upper limits, and the penalty due to the inequality constraints about the lower limits. Because each such equation corresponds to 2 inequality constraints. So finally, how many multipliers we need to introduce? We introduce 1 lambda and nj mu's and nj gammas. So finally, we have originally we have ng x, right? We have 1 lambda. We have ng mu. We have ng gamma. So we have 3 ng plus 1 total variables. We actually largely extend the dimension of the problem. Then we need to calculate the gradient vector for the L function. First, let's calculate the element with respect to p and lambda. So those have to be 0. There's no room to negotiate. So which means the L function in the increase the higher dimensional space, at least in the dimensions about the p and the lambda, they need to look like stationary points. Okay, but for the other in the other dimension about the mu and the gamma, we don't know. We need to utilize the KKD condition to decide what they look like. Partial L, partial P means you just calculate directly calculate the partial L with respect to P, and this one is equal to just dc by dp. And because in this L function, we only keep the items related to pi. So to check which one related to pi. So this one is related to pi. So there will be, there's a negative sign, so there will be a negative lambda. And this item also related to pi. So that's a positive mu. And this item related to pi, there's a negative sign, so it's a negative gamma. Okay. So we have the first equation, which is similar to the early equation we had, but there's two new items, the positive mu and the minus gamma added to this equation. We can just put the equation here. The second is a partial L, partial lambda, that's same. That's just same as the equality constraint. It's power balance. There's nothing new. And the third and the fourth one will be tricky. So we have inequality constraints. So that may not be zero, which means they may not be at the stationary point. So we have to utilize our KKT condition to decide how we're going to address those two items. So KKT condition says for each inequality constraints, in this way, we have add three things. The first one is the inequality constraints itself, right? Remembering we show first is if the inequality constraint itself is equal to 0 or less than 0. The second, the multiplier has to be non-negative. The third one, the u and the mu has to be always 0. Okay, so we need to add those three things for each of the elements related to a partial L, partial mu, or partial L, partial gamma. So we just put them into here. So this is the number one. That's the inequality itself, right? And those are the number two. That says the multiplier cannot be negative. Then those are number three. They said the product have to be 0. So if you want to program a solver to address this problem for any dimension, those are what you need to figure out in the code. But when we deal with lower dimension problem, it's better just to check every possible scenario to make sure each scenario can be satisfied. So here, we just go ahead to study three typical scenario. The first scenario is the generation of the unit I is not reaching either limit. Okay, it's less than the upper limit and higher than the lower limit. If this is the case, I don't need that mu and the gamma at all. There's no penalty, or in other words, there's no penalty. The second case, the generation is reaching the upper limit, exactly at limit. If this is the case, to make the product to be 0, the mu cannot be negative, and product to be 0, so the gamma has to be 0. The gamma is not needed. And the third one is the generation is at the lower limit. If it's at the lower limit, so the inequality constraints about the upper limit is not required. So the mu can be 0, and gamma cannot be negative. So the gamma together with this one will form this KKT condition. Okay, so that's a very mathematic, but let's try to understand what happened here. For the first scenario, if mu and gamma are 0, so we can just take away those mu and gamma. So this one will be exactly just the first order derivative of the cos with respect to generation to be lambda. This is exactly same as our problem without the generator limit, right? It tells all the generators, if they are not reaching the limit, they need to have the same incremental cost. So think about a problem. Even I gave you the upper limit, lower limit, but when you try to dispatch all the unit, none of the unit reach any limit. So which means even the limit are there and not applied to your solution. So basically, you are solving a no limit problem. This is what it tells. So it's still, if any units they're not reaching the limit, they need to operate at the same incremental price, same incremental cost. So what if one unit is reaching the upper limit? The second case. If that's the case, mu will be 0. So we need to cross off mu from here. But because, because of lambda from here, lambda will be 0. But because mu is a non-negative, so this one means if for such a unit reaching the upper limit, their actual incremental cost cannot be higher than the equal incremental cost, equal price. So they need to operate at slightly lower price to be able to reach the upper limit. So for a unit, in order to reach the upper limit, they need to operate at a price cheaper than the equilibrium. So that sentence sounds reasonable. It's actually very logic, right? If you want to make a unit to generate at its maximal, it has to be cheaper than the other unit. So that's what this sentence is talking about. For the third scenario, when mu is 0, we just cross off the mu from the original equation here. So for that unit, the price will be lambda plus gamma. Gamma is positive, which means this one cannot be lower than lambda. So lambda is actually the equilibrium price. And for such unit reaching the lower limit, this price should be higher than the equilibrium price. This says if a unit is more expensive, we can only allow that unit to operate at the minimal value. We don't allow it to generate more. So the physical meaning is those three sentences. All units operating within limit, if they're not reaching either limit, they have to have an equal incremental cost, which is lambda. And this lambda is solved using a similar approach as we did for the formulation without limit, either by approach number 1, by step 1, 2, 3, or do the iteration. If we found any unit operating at its upper limit, which means this unit should be cheaper. It cannot be more expensive than lambda. Otherwise, it doesn't make sense. If this final unit is, if it's very cheap, it's cheapest one, we want to first make sure this unit to generate the maximum power, right? For the remaining part, we'll do dispatch. Similarly, for some unit, I think should be not cheaper. If a unit operating at a lower limit, they are not cheaper than lambda. If this unit are more expensive, they can only output at their minimal value. We don't allow them to generate more, right? Maybe a typo, just missing not. Okay. Is that clear? Okay.
Gamma is market price.
Lambda is the price. Lambda is final price. Lambda, mu, gamma, they all mean penalties. Okay. Lambda means the price. Physical meaning of lambda is price. Gamma, the mu is the penalty of violating the limit. So lambda is the penalty violating the electricity balance. So that's why the lambda means price. Let's see what happened on this example. So that's about the same example. The only thing we change, we increase the load of the system from 800 to 975. So when we have load 800 megawatt, right? So we will know that market price is $8.5 per megawatt hour. So there will be 3 intersection points. So the total will give us 800. But now we increase the load. So which means this price is wrong. But if we borrow the idea from the Newton-Raphson approach, we can start iteration. Let's use this $8.5 as our initial guess for the lambda. So this one need to move up, right? When we move up, all the intersection point will move to the right. So we'll increase together. We increase output. So move up. So if we move up to this position at the yellow, at this point, it reach the limit, the upper limit of the third unit. The third unit is it's not number 1. Yeah, this one is the cheapest one because it has a smallest slope. By increasing the same amount of power, this dollar amount increase the slowest. So when we reach this position, is actually intersect at the maximal point for the unit number 1. But unfortunately, the total intersection point, if you add those value, it doesn't give you our goal. It only give you 906. It's still a certain gap. But for this unit, we cannot increase further. We cannot go beyond. We cannot, that will be wrong. That will damage this unit. So the unit number 1 will be fixed here. So we decided the output for the unit number 1. But for the other unit, we need to further increase. When we further increase to this position, we have for the unit number 2 and 3, we'll have 2 intersection points. So if I add those values together, give you 975. Okay, so that is the final solution. All right, so this explains why we need to deal with such an inequality constraint in the formula in the ways from previous slides. Okay, just to summarize, if you move when you solve the problem with equality constraints and inequality constraints, if you use the Newton-Raphson approach or borrow the idea from Newton-Raphson approach, you can start from any initial guess of the price. Basically, you just draw a line. You just draw a line. You start from any initial guess. Okay, then you collect the intersection points. The total, there's a certain gap. If it's smaller than the load, you just move up the line. If it's higher, then you just move down the line. So until the total intersection point reach the load. Meanwhile, if any generator reach the limit, you just stop there. Don't move that point anymore. Just but do the changing for the other units. Okay, until you have a intersection point together, make up the load. Yeah, that's let me just pause here so we can continue on one side. Yeah, this is let me finish this scenario. So let's say if my load actually increase even to 1025. So you see the second unit reach a limit, and third unit reach a limit. That's the total load I can generate. Or another scenario will be if I move down, I want to reach this load. If this unit reach a lower limit, you need to stop here and dispatch for the other 2. Okay, so you will have like a piecewise linear curve moving up and down to intersect with all the incremental cost curve, and together the intersection point will give you a total load. Then you'll find the solution. All right, good.